Okay, so welcome to the Tutte Colloquium. We're very happy to have Sophie here. So Sophie, I guess everyone knows. So she graduated from Princeton 2018 and then worked as postdoc in Rutgers and Princeton afterwards. And last year she joined our department. So Sophie's researches in structured graph theory, and she's going to talk about induced subgraphs and Treewidth. So take it away, Sophie.
Thank you. Thank you all for coming. Thank you for having me. So I'm talking about induced subgraphs and Treewidth, and this is a project joined with Tara Abrashami, Maria Trudnovsky, Jamil Debek, Seper Hajabi, Pavel Janjevsky, and Christina Vuskovic. And what I'll talk about is a bit of an overview of the whole thing, and then I will tell you some of the ideas for one specific result, which is joined with Tara, Maria, and Seper. So let me start by showing you a picture of what Treewidth is, and I will tell you the truth behind it on the next slide. But just so that you have something in mind when you see the definition on the next slide, Treewidth is a graph parameter, and it is some measure of the complexity of a graph that played a very fundamental role in the graph minors project of Robertson and Seymour. And in the very loosest terms, it means how much a graph is like a tree. So if you look at this graph, then here are a bunch of colorful sets, and the way these sets interact is in some sense encoded in this tree where we have a vertex for each colorful set. And so if a graph has small Treewidth, we like that lots of algorithmic problems can be solved efficiently if Treewidth is small. And therefore, it's a natural question to ask, what causes large Treewidth? And part of the graph minors project was an answer for that in the context of graph minors. So with that, and roughly thinking of this picture, here's the actual truth about Treewidth. So what you saw on the previous slide, the picture in the middle with the colorful sets, is a tree decomposition. A tree decomposition of a graph means a grouping of vertices of the graph in a tree-like fashion. In the following sense, it consists of a tree, and this is not a tree in the graph itself. This is any tree that does not have to occur in the graph, is not related to the graph at all. And beta, which is a set of bangs, and these are the colorful sets you saw on the previous slide. So T is a tree, and beta consists of, for every vertex of the tree, you have a subset of the graph. So here, the gray picture is T, and then beta is, for example, the red vertex maps to the red set. And to show how this encapsulates the structure of a graph, there are two rules for how vertices must occur in bangs. The first is that whenever you have an edge in the graph, there has to be a bang containing this edge. And the other is that whenever we have a vertex in the graph, then if you look at the tree and look at the bangs that contain this vertex, this should be non-empty and it should be a subtree, so it should be connected, which means if you have a vertex in different bangs, it also has to be in every bang on the path between them in the tree. So looking here, you can see from the middle picture that for every edge of the graph on the left, there's some colorful set that contains it. But also if you look at this vertex of G, for example, it's contained in 4 bangs: brown, this medium dark blue, orange, and pink. And indeed, brown, medium blue, orange, and pink forms a connected subgraph of the tree. And assuming that my picture is actually a tree decomposition, the same will hold for every vertex. Whenever we look at a vertex here, the bangs that contain it form a connected subtree of the tree on the right. And so one consequence this has is that this is sort of a structured collection of sets that separate the graph, right? For each of these bangs that aren't on the very outside, if you delete it, the graph falls into connected components, and the way these components interact has to do with the tree. And that's what makes this useful for algorithms, because you can do tree-like dynamic programming. So we want to find these things where bangs are small. In general, the width of a tree decomposition is the maximum size of a bang, with a -1 here. And I will tell you on the next slide why there's a -1. And then the tree width is the minimum width of a tree decomposition. Right, so a tree decomposition is an organization of the graph into bangs that make a tree-like pattern. And we want to find such a decomposition with as small bangs as possible. And here are some simple examples. The first is that if you have a tree, it has tree width 1. And that's the main reason why there's a -1 on the previous line, so that trees are actually the most tree-like things with tree width 1. For example, in this tree, you get this tree decomposition. And then for tree width 2, you can tell that your graph has to have a cycle. And if we have a cycle, we can find a tree decomposition of tree width 2. Like this, right here, we have all bangs of size 3, and they're arranged in this pattern. And most of the vertices occur in 2 adjacent vertices of the tree. And this one is in all of them, but for each one, you see that it's connected. So this is the very beginning, right? Tree width 1, trees, tree width 2, something that has a cycle. But what in general tells you that a graph has large tree width? Oh, and I should say, ask me questions throughout if you have them. This is a talk where I'm telling you lots of things that you may or may not be familiar with, and please ask me if I'm not making sense. Okay, so in the graph miners world, there is a somewhat precise answer saying with some degree of inaccuracy that a graph has large tree width if and only if it contains a large wall as a miner. And this is a picture of a 4x4 wall, and you can imagine how you would make this bigger in both directions, and that gives you graphs of increasing tree width. And if a graph has really huge tree width, then it's guaranteed to contain a large wall as a miner. And that actually also gives you an answer for subgraphs. So in a subgraph, you're allowed to delete edges because it's a standard result about minors. Then if you're a graph like this one, which has all vertices of degree at most 3, then containing this as a minor is the same as containing a subdivision of this as a subgraph. So if we're asking about minors, what causes large tree width? It's walls. And if we're asking about subgraphs, it's subdivisions of walls. And so my question is, what happens for induced subgraphs? So induced subgraphs means you're not allowed to delete edges. You're only allowed to delete vertices. And you're also not allowed to contract things, but we're not even mentioning that here. And then, you still have walls, right? That's a thing that could happen. And you still have their subdivisions. And again, that's one of the things that we should expect as an answer. Curiously, what you get now as well is line graphs of subdivisions of walls. So this is a line graph of a subdivided wall, where line graph just means you make a vertex for every edge and make 2 of those adjacent if the edges share an end. And these 2 things, neither of them contains a large instance of the other, because if you look at this, it has triangles, whereas this one doesn't. And so this left one doesn't contain the right. But the right one has vertices with 3 pairwise non-adjacent neighbors, claws. And line graphs are claw-free, so the right also doesn't contain the left in the induced subgraph sense. So these are 2 of the basic types of answers you should expect. And is that all? No, you can't delete edges. And so you should expect that there are some really dense graphs that come up as answers. In particular, a complete graph. If you have a complete graph, then there's a standard result about tree width that actually it has to go all in the same bang. And so a complete graph has large tree width. And also complete bipartite graphs, which just means two vertex sets and all edges between them. And again, these four things, subdivided walls, their line graphs, complete bipartite graphs, none of them contains a meaningfully big copy of any of the others. So all four of these are things that cause large tree width that are different from each other, and neither of them can be omitted as an answer. So is that everything? That would be nice, but no. And I will tell you what's actually happening in this picture. But also this is your first taste that for induced subgraphs, the truth is messy. So this is a construction that doesn't contain meaningfully big copies of any of the other things. It's due to Centiari and Trottignon, and it's called a layered wheel, and I'll tell you briefly how it's built. And then this picture took a while to make, so I'll use it throughout the talk to explain how what I'm saying relates back to this picture, because this is somehow capturing a part we don't understand very well yet. So this is a construction where you start with one vertex and then you build a path, and then you build another path and another. And you keep going, but it grows exponentially. So I didn't even do 4 complete layers here. But what you do is, for a path like this, there are 2 kinds of vertices. This guy who has a neighbor above, and this guy who doesn't. So for the ones who have a neighbor above, what we do is what you see here. If he has a neighbor above, he gets 3 neighbors. Then we put 3 neighbors of his neighbor above, and then 3 more neighbors of him. Whereas for him who has no neighbors above, we just put 3 neighbors of him. And then having done that between all the neighbors we put in a row along this path, we add 1 vertex between every 2 consecutive ones. And that gives a construction of large tree width. Because if you look at the layers, every time you add a layer, you roughly add 1 to tree width. But it's kind of not as bad as the others, because as the graph grows, tree width grows kind of slowly. And somehow one thing I will talk about is how that is a truth about a certain class of graphs. Another thing is that these have vertices of huge degree, right? If you think back to walls, they didn't have vertices of degree 4 in them. But here, this blue vertex will gain more and more neighbors on each layer. So it'll have tons of neighbors if you want large tree width. But it doesn't contain any of the other stuff really. So this example kind of motivates a bunch of things we could ask, like, does tree width grow that slowly if we don't have the other things? Or does tree width at least grow slowly if we don't have big degree and don't have walls in their line graphs? So those are the 2 conjectures that, based on the information I showed you so far, would be reasonable and maybe true. The first is, what if we look at a graph of large tree width and put some constant bound on maximum degree? Then we don't get layered wheels, and we don't get big cliques or complete bipartite graphs. So maybe then the actual truth is just walls and their line graphs. And this is still open, but it's proved actually in somehow a mixed case between the 2. The same team of authors proved that if G also doesn't contain some fixed graph H as a minor, then this is the truth. And the second conjecture says maybe, things like layered wheels are the only way to make tree width large. That's not these 4 initial things we described. So maybe if you don't contain these 4 things, where I mean some big copy of one of these things, then all you can do is have Treewidth grow logarithmically in number of vertices. Right, what happened in layered wheels is we found something different with large Treewidth, but to make Treewidth bigger, we needed to add a constant factor, more vertices. In other words, layered wheels have logarithmic Treewidth, and maybe there's a truth in that. If Treewidth of a graph is actually much more than logarithmic in the number of vertices, then maybe it's one of the four somehow well understood families of things that give G large Treewidth. And so I'll tell you some things that are known towards both of these. First, and just feel free to ignore the words and look at the picture. If we bound maximum degree by a constant, and if we exclude even induced cycles, then Treewidth is bounded by a constant. That depends on what degree we choose here. And this makes some amount of sense because if you look at subdivided walls and their line graphs, then one of the first kind of interesting things they contain are even induced cycles. And then here's a bit more, but again, it's sufficient to read the pictures. If we bound maximum degree again, and now we exclude three more things. One of them, actually, a line graph of a subdivided wall. And then these other two, which are first a theta, where a theta means two vertices and three paths between them. And a pyramid, which is a triangle and a vertex and three paths between them. Then Treewidth is bounded by a constant. And here we can even ask that the paths are at least some constant length. And this makes sense because if you picture a wall, then this is the kind of thing that occurs in a wall. And this one we would very much like to get rid of, but can't at the moment. This doesn't occur in any of the things I've shown you so far. But unfortunately for this to work, that's another thing we should exclude. Here's something that is a bit different, but I like it because it's symmetrical, right? It contains a big piece of a wall or a big piece of the line graph of a wall. So again, we're assuming we have bounded degree. And now exclude all subdivisions of a cubic caterpillar, where a caterpillar means a path, and you can add paths, but only by putting one end of each path you add on this original spine of the caterpillar. And in addition, we don't want to make vertices of degree 4 because we know that walls are one of the things that should be captured by this theorem. And also, we exclude the line graphs of this caterpillar and its subdivisions. Then we get Treewidth bounded by a constant. And so these are, this is the kind of thing that you'll find in a wall. And this is the kind of thing that you'll find in the line graph of a wall. So this is kind of, if you think about it, it looks like it wants to be the first layer of a wall, and then we should add a second. So this is what we know so far about bounded max degree and trying to get a constant bound on Treewidth. But the thing I want to tell you a little bit more about is this. So now what will happen is we will prove a logarithmic bound on Treewidth. And what we need to exclude for that is the series of pictures here, a complete graph, a theta, which you already know, two vertices with three paths between them, each of length at least 2, a pyramid, which is the same, except you have a vertex and a triangle, and now one of the paths is allowed to be just an edge. A prism where you have two triangles and each path is allowed to be just an edge. And this, which looks like a prism with one path is length 0. And I'll tell you a bit more about this, and it will make more sense why we're excluding these things. But one thing that's interesting about this to me is layered wheels don't contain these things. If you look back at layered wheels, and the picture will actually come back, they don't have 3 pairwise adjacent vertices, so anything with a triangle is not part of a layered wheel. And then Cynthia and Trotino also showed that they don't have thetas, which means for this class of graphs, logarithmic treewidth is the answer. Right, layered wheels show that in this class of graphs, logarithmic treewidth can occur. It's a lower bound, and this gives it up to a constant matching upper bound. Which is strange. I don't know any other class of graphs where logarithmic treewidth is the truth. And so I want to show you a bit of the proof, because there are lots of different induced subgraph techniques that you wouldn't necessarily expect to go into this that fit together here. And since we'll cover a lot of different topics, if something doesn't make sense, feel free to ask, but also what I'm talking about will change every few minutes. So hopefully there will be something in here for everyone. Here's a very rough plan, and I'm highlighting words that I haven't explained. For now, let's assume we're in this class of graphs. And then our main enemy will be things called wheels. So first we'll look at what if there are no wheels, and we'll show that then life is good. The graphs are nice, they actually have constant treewidth. And then we'll say, okay, we don't like wheels, how can we break them? And we'll show that wheels break apart the graph. And then we'll try to say, let's break apart the graph in the right order. That gives us pieces at the end that fit together nicely to make a tree decomposition, right? If you think back to the first picture, a tree decomposition is cut sets. And they're cut sets with a certain structure. So if we can get cut sets from wheels and get them to fit together well, that's almost already a tree decomposition. Here's a wheel, and roughly a wheel means a cycle and then a vertex V called the hub with at least 2 neighbors on the cycle. And there are a few technicalities about if these neighbors are too close together, we don't like it. It's not really a wheel. But roughly, this is what a wheel is. And many wheels where V doesn't have a lot of neighbors, like this one, and that one, they're actually instances of things we exclude. So in a wheel, we can assume that V has at least a few neighbors. And that's helpful because those neighbors will help us break the graph. If you look at layered wheels, and it's no accident that wheels are enemies and layered wheels are the construction, that shows things, then this thing is full of wheels. Like looking at this cycle, this pink vertex has a lot of neighbors in it. But also vertices and their neighbors tend to break the graph. If you look at blue and picture deleting blue and its neighbors, then this part of the graph would be kind of stuck. Right? This is actually a neighbor of blue, so this part of the graph couldn't get out. So while blue has a lot of neighbors, those neighbors allow us to decompose the graph into lots of parts. And that's what we're going to do. I'm going to say if there's a wheel, it should break things and break things apart in a graph sense, so in a useful way for us. Why do we get wheels at all? So again, Treewidth is about finding nice cut sets. And if you look at a cut set in a graph, let's make it minimal in the sense that if you delete more stuff, it doesn't give you the same cut anymore. Then what happens is this is your cut set, and you'll have components of the rest so that every vertex of X has an edge to that component. Because if this vertex had no edge to D2, we could put it in D1 instead of X, and it was still separate. And so now, this is the slide where it may finally make sense why we have this particular list of things that we exclude. If you look at a cut set, and you picture it having 3 pairwise non-adjacent vertices, then you can say, well, how do these connect through D2 and how do they connect through D1? And the truth is, if you have 3 vertices and they connect through a component, there are 3 main ways this can happen. This way, or that way, where I mean there's a path here and B has lots of neighbors on it. And so if you do this in D1 and D2, it means you pick 2 from these 3 and put them together, one on the left, one on the right. And in many cases, this gives you one of our 4 excluded things. If you get 2 of this, one on the left, one on the right, you're getting this picture. If you get this on one side and this on the other, you're getting this picture. And 2 of this will give you this one or that one. So what does this mean? Well, if we have a minimal cut set X, and it has 3 pairwise non-adjacent vertices, since we can't actually get these, what happens must be this outcome. So one of the 3 vertices is a wheel hub, right? If you picture this on the right and this on the left, then it looks like a wheel. So in our setting, minimal cut sets can only have big stable sets because of wheels. And there's a way to turn these minimal cut sets into 3D composition. And this is a thing called PMCs. PMCs come from a fairly different context. They are from trying to compute the minimal chordal fill-in of graphs. And if these words mean nothing to you, then that's okay. That's why I didn't even write what PMC means on this slide. It will not matter to us, but PMCs connect minimal separators to 3D compositions, right? 3D compositions don't consist of minimal separators. They consist of things that are somehow bigger than minimal separators in meaningful ways. And PMCs encapsulate that bigger than minimal separators property. And for our purposes, it's enough to know that each 3D composition can be built from PMCs, and that if we have a PMC and it has a large stable set, in fact 4 vertices are enough, then at least one of them is a wheel center. And this follows from applying the previous minimal separator thing in the context of PMCs. Why does that matter? Because we don't have a big clique either. So if you look at a PMC and you apply a Ramsey, then you will get a big stable set in it since you don't get a big clique. And then you figure out that your PMC contains the wheel center. So if we don't have wheels, PMCs are small and we have bounded Treewidth. First step already done. Right, I know that PMCs seem kind of out of nowhere here, but they tell us that things are easy, things are nice if there are no wheels. So what is the problem with wheels? Well, we want to use wheels to break the graph apart, and there's one case where wheels don't break the graph apart, and this is called the cube, and the cube is drawn here in a way that's not very cube-like to show you that in fact it's a wheel. This part's a wheel, and because this vertex has neighbors in each of these sectors, this wheel center plus its neighbors don't break things apart. But with some effort, you can show that this is the only problem. In our class of graphs, wheels can always be used to break things apart unless you have a cube. And in our class of graphs, you can also show that cubes are kind of isolated occurrences. They can happen, but when they do, they don't connect well to the rest of the graph. And so for finding a tree decomposition, you can basically ignore them. So with that in mind, let's pretend that our graphs don't have cubes. Then here's the slide that finally formalizes how wheels break things apart. So a star cut set is what we've been looking at for a bit. A cut set you get from deleting a vertex and some of its neighbors. And the thing is, in our class of graphs, if you look at a vertex V, that's a hub for a wheel, and you delete V and its neighbors, then the wheel breaks, in the sense that in this other picture where we deleted V and its neighbors, there are some components you get in the rest. And each of them actually only contains one of the green, pink, and yellow set. So in particular, it breaks the graph apart. And now we might say, after breaking the graph, let's look at this bit and that bit separately. But what happened is the wheel broke. So in each of the separate parts, V is no longer a wheel center. So if we could do this everywhere, for every vertex, do this kind of decomposition, then no vertex would be a wheel center, and that would mean we have no wheels. And if we have no wheels, we're happy. This seems to be true for most problems in graph theory. But here in particular, if we have no wheels, we're happy. So how can we do this? How can we break the graph apart at every wheel center? Here's something else. This is a theorem of Kuhn and Oster's, and it comes up somehow more in the context of chi-boundedness. But what it says is, if you have a graph with large average degree, then you should contain pretty much any graph you want as an induced subdivision. Unless you don't, but the reason why you don't is always the same. You get a complete bipartite subgraph. So in other words, if you don't have a big complete bipartite subgraph, which we don't because that would be a big clique or a theta, and if you don't contain a subdivision of some graph, then you have bounded average degree. So how does that help? Well, this tells us in which order to decompose things. What we want to do is decompose first at vertices of small degree, because we look at their neighbors, right? So if they have small degree, that's a small cut set. And then later, figure out what to do with vertices of bigger degree. And this works. If your graph has bounded average degree, then half the vertices have degree not much bigger than the average degree, so put them in one set. And then in what's left over, do it again. This gives you a logarithmic number of sets. And for each vertex, its neighbors in future sets that were made later are only a handful. because we started by deleting vertices of small degree. And then in what's left over, we found vertices that now have small degree. So they might have lots of neighbors in the previous set, but not a lot of neighbors going forward. And then do it again and do it again. And since each set has bounded degree, we can color them to actually split them up further into stable sets. This is where logarithmic treewidth comes from. It comes from the fact that in the other results, we were bounding maximum degree, and here we aren't. But we still can get this partition that in useful ways functions as though vertices have bounded degree. They have bounded degree sort of when their time comes. We'll first decompose by the first stable set, vertices of small degree. And then at the next step, we'll know something about those vertices. And so we'll be able to handle even if a vertex in the next stable set had a lot of neighbors in the first one. Let me go to where this hopefully makes a bit more sense. Well, so we have these sets. They're ordered in a specific way so that we have control over vertex degrees. And now we'll decompose by each of them. And that decomposition is exactly this thing about wheels, where we break wheels that are centered at a given vertex. If we decompose, there are two main things that can happen. Either when we look at a vertex and the cuts that it gives us, it cuts up a little bit of the graph, or it cuts the graph into small chunks. And these cases are handled separately. And then at the end, once we're done, we'll have killed all wheels, treewidth will be bounded, but we'll have a bunch of stuff that we cut off the graph along the way. So we need to deal with that and figure out at the very end, treewidth is small, but now how do we stick the rest of the graph back on in a way that's consistent with the tree decomposition? And that's the plan. Let's first look at what happens if I have one vertex and its neighbors, when you delete them, break the graph into lots of small parts. Well, that we actually really like, because this is starting to look kind of like a tree decomposition. We have this thing and it's cut off by its neighbors, and this thing, and these are all small. And here small means that the size went down by a factor of 2. And again, that's useful for logarithmic. Right? To apply induction to something that's logarithmic, we need to reduce by a factor of 2. But here we can. And so that's what you do. In these parts, you apply induction. And then you just need to deal with how do they fit together. And as it turns out, how they fit together is a wheel-free graph, essentially. So how they fit together is very, very well controlled. So you decompose each of these things and then use this to guide you as to how the different components should be stuck back together with each other. You have a tree decomposition for each, and you take this graph where each component was contracted to a vertex to have a pattern for combining all the tree decompositions of little parts into a tree decomposition of the whole. The more interesting case is when a vertex only cuts off a little bit. And again, don't look at the words, look at the picture. If we have a vertex V and delete its neighbors, and there's a huge component that still contains more than half of the graph, then all the other components are kind of little. And so what we need to decompose now is the big thing. The little ones, induction will handle them. They're fine, we don't need to worry. And something nice happens here. Because if you look at the set and look at all these things at the same time, right? We have a stable set, a huge set in the graph, and we want to decompose along all its vertices. And for each of them, we have a cut set and we have a big part. But what happens is the big parts line up. And again, look at the picture. This is sort of a joint B side for all of them. The big side, they all agree this is the part of the graph where things are bad. This is the big part where we need to work more. And then each cuts off its own private little bit of the graph. Which we need to make it tree-like, right? If they all cut up a little bit of the graph, each one said, in this part I can apply induction, but actually all the little bits formed a big clump that had big tree width again. We wouldn't be able to use it as much. But here, each vertex in the stable set has one big clump, and all the little bits, they kind of lead a life of their own. They don't attach to any other vertices little bits. So picture this being the first set in our logarithmic sequence of sets we wanted to use to decompose. We can decompose by all of them and go to this, the thing that they jointly agree is the big part, and do all of the little parts separately by induction. And this is sort of the key thing. At each step, we don't pay for decomposing by all the vertices in the set. Since they all have decompositions that align in this way, we only pay once for decomposing by the whole set. So that's the whole plan. And right, we have an ordering of vertices that tells us in which way we want to decompose them. Start with the ones of small degree, and then the ones of small degree going forward, and so on and so forth. Small degree means that this set is small, which is good because it looks like it wants to be a bang of the tree decomposition. And then at the very end, having done them all, we have broken every single wheel in the graph. So at the very end, there's a graph of small tree width. And now we go back up the hierarchy, putting back what we cut off in each step. But what we cut off in each step fits nicely. So if we have a tree decomposition of this, then we just augment it a little bit. We take for each of them a tree decomposition. And now we just need to make sure that the adhesion between the outside set and the inside set is actually what it's supposed to be. And this is the one last time that wheel centers come into it. In the middle, the vertices called U aren't wheel centers because what we just did to get to the middle is break all their wheels. So that means in the middle, if we found a tree decomposition, each bag has few of these guys. Because recall from the very beginning, if a PMC has many vertices, then one of them is a wheel center, but none of these are. So that tells us that in the tree decomposition for the middle part, we only need to correct each bag by a constant amount to account for putting these things back where they belong. And so this is what we did. I know it was a lot to absorb, but there's somehow no way to tell you meaningfully what this proof does without telling you lots of different little tools that somehow work together. So what we did was first we investigated wheels and we said if there are none, life is good, because then the theory around PMCs just tells us that we get a constant bang size tree decomposition. So then we went back to wheels and said, okay, these aren't good for Treewidth, but do they do something for us? And it turns out they do. What they do for us is they give us cut sets. And we like cut sets because tree decompositions at their heart are structured cut sets. But then we said, we want to break all wheels, so we kind of need to decompose by all these cut sets, and that may be a mess. So then we use the next tool saying, but we have degree bounds, and these bounds on degree tell us in which order to use the different wheel hubs to decompose, which matters because bags are cut sets, and so the cut sets we use should be small. And if we use a vertex and its neighbors, therefore it better be a vertex of small degree. So we decomposed a lot, and then we were at the end. Now the wheels are gone, and we have a Treewidth, we have small Treewidth, and now we only needed to pay for putting the rest of the graph back. And for that, the main tool was noticing that for each step when we decomposed, we might have decomposed in a lot of places, but these places don't interfere with each other. They can all be put back in a way that doesn't hurt us, in a way that makes the bangs bigger, but in a very controlled way because they each stick out in a different place. And so we can basically put each thing that stuck out back into a different bang, and that is acceptable. And so at each step, we, at the end, we had constant Treewidth, and for each step that we put back the graph, we pay a constant number for how bang size increases. And that's where logarithmic comes from. But then that's a tree decomposition of the whole thing. And here I wrote gives algorithms, which I just want to mention very briefly. A lot of Treewidth algorithms use dynamic programming. And so a lot of them are singly exponential in Treewidth, because what you do is basically for each bang, you say, what are all the things that could happen here? And if you think of finding a stable set in a bang, then you look at each subset. And so that's singly exponential, which means constant Treewidth is wonderful for all sorts of algorithms, but many things that we care about are singly exponential. And so there's still polynomial time if Treewidth is logarithmic. Because if you have something that has running time constant to the Treewidth and the Treewidth is logarithmic, that's polynomial in the number of vertices. So this works for finding a maximum weight stable set in this class of graphs. It actually works for coloring because we have bounded average degree. So chromatic number is bounded by a constant. And if you're coloring with a constant number of colors, again, singly exponential. So somehow logarithmic Treewidth is nice because it has many of the benefits that normal constant Treewidth has. Many of the algorithms work. And also, in what seems like an extremely lucky coincidence, you can approximate Treewidth. You can actually find a tree decomposition that's not much worse than the best one in singly exponential time. This is part of what Robertson and Seymour proved, is you can find a good enough tree decomposition for these algorithms. So somehow logarithmic Treewidth works, it just fits, it's still polynomial, anything bigger wouldn't, but this gives algorithms right away. Okay, and possibly as a reward for listening for this entire time, here's my favorite picture again. You can also possibly see that it occurs a lot in and around me. Yeah, thank you.
Thank you, Sophie. So any questions for Sophie? Maybe I'll ask one first then. So is this logarithmic in the number of vertices the best possible, or as an upper bound, like in terms of the multitude? Sorry, yeah, the asymptotic.
Yes, right, good point. That's what this picture tells you, in fact.
Because this one excludes those structure, but does reach logarithmic bound.
Right, so for this class of graphs, logarithmic is the right answer, which
I see.
Feels strange.
But if you have some graphs with smaller tree width, but still maybe it's growing or something, is it possible to get characterization? It has to exclude this, but is there any research in there?
That would be great. The problem with layered wheels is that this is one of the constructions, but they have a second one that excludes different things. And so at the moment, it feels more like layered wheels are a family of constructions. And it's hard to say how to describe all layered wheel type constructions. And you would need to exclude all layered wheel type constructions. For example, this one, although I'm sure from just the picture on my board and the picture on the slide, you cannot appreciate this at all, but this one excludes evenholds, and it's fundamentally somewhat different. They're both due to Centiari and Tortinium, but this one's more complicated and it shows other things that you also need to take into account. So ultimately, that would be great if we could find the actual answer for what all these things look like, but it seems to be complicated.
Okay, but if there's a next step, what kind of order would you consider?
I mean, one of the next steps then
like it's smaller than log, I guess smaller than log n, but maybe not all the way to powers of log n, smaller than 1 power. Is that something reasonable to even think about?
That seems hard. Like it already was kind of weird that log n came up in this proof. One thing that would be nice is there was one result that I showed you where we got line graphs of subdivided walls, but there's never anything where we actually got a subdivided wall to come out. So one thing would be to find literally any of these settings where we say it's this, 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 or a subdivided wall. So far, building walls is hard. Building line graphs of walls is easier somehow because they come out when we're looking at line graphs, and looking at line graphs is similar to looking at subgraphs instead of induced. But there's nowhere where we actually can say, look, here's a wall. Then, I mean, I don't know which assumptions we need to add to that to make that happen, but it would be nice to have a result that has that as the outcome.
Thank you. Other questions?
Yeah, Sophie, I was wondering, there's one of the nice proofs of the grid theorem involves this disentangling of connectivity with a given collection of paths. Have you thought about anything like that for induced subdivisions?
Yeah, but it's you can see there are attempts here to see if we can do this with there's a bound on max degree. Layered wheels kind of show, right, the complete minor you'd get is taking each path as a set. And that shows one of the ways that untangling is hard. So yeah, for a while we hoped maybe we can untangle it if degree is bounded, because fundamentally what seems to make untangling hard in layered wheels is that every connection is interrupted by neighbors of somebody else. So if degree is bounded, maybe that doesn't happen, but even that we don't know how to do yet.
Okay.
Right. There's some hope to untangle if we have a complete minor, but there aren't very many edges for each pair of sets. But if it looks like a layered wheel or like this kind of bounded degree attempt at a layered wheel, we don't know yet.
Thanks.
Okay, thank you, Jim. Other questions? Okay, so maybe we can leave more questions during the discussion time. So let's unmute ourselves. Okay, and then give applause to Sophie.
Thank you.
Thank you.